In this tutorial, we'll take a look at the Stencil Buffer and how we can use it to create useful effects such as outlining a model. So the Stencil Buffer, just like the depth buffer, holds a value for each pixel you can see, these values being used for image masking in general. Unlike the depth buffer though, where each pixel holds between 2 and 4 bytes of data, for the Stencil Buffer, each pixel holds 1 byte of data, so values from 0 to 255. But you'll mainly only use the values of 0 and 1. So let's look at how we can work with this new buffer. First of all, we have the function glStencilMask that allows us to choose which parts of the stencil buffer we want to be able to modify. It simply takes a pixel from the mask and the corresponding pixel from the stencil buffer and applies a bitwise AND comparison on them. Keep in mind, each pixel has a byte of data, so 8 bits. A bitwise AND operation compares each bit with its corresponding counterpart and only outputs 1 if they're both 1. Therefore, if we input 0x00 into glStencilMask, which means that we have 8 bits equal to 0, then all the comparisons will fail and the stencil buffer won't change at all. But if we input 0xFF into glStencilMask, then all the bits of the mask will be 1, since 0xFF is equal to 8 once, and so we'll be able to modify any part of the stencil buffer. Now let's look at two more functions we can make use of, glStencilFunc and glStencilOp. glStencilFunc allows us to control how the stencil buffer passes a test or fails a test, while glStencilOp allows us to dictate what happens when the stencil test fails, when the stencil test passes but the depth test fails, and when both pass. Let's take a deeper look at glStencilFunc. It takes in 3 arguments: a function, a reference value, and a mask. The function can be one of these, by default being set to glAlways, so the test always passes. The reference value is simply the value we use to compare in the function. Notice how before comparing the stencil value with the reference value, we apply a bitwise AND operation to both using the mask. This means that if we want to compare the numerical value of the two accurately, you will want your mask to be 0xFF so that nothing changes. Now for glStencilOp, it has 3 arguments: sFail, dpFail, and dpPass. These stand for stencil fail, depth fail, and depth pass. For all of these, you can choose between the following options. By default, they all have glKeep, which basically means that nothing changes. There is not really much more to say about these functions, so if you want to know more about them, look them up in the documentation. The stencil buffer can be used for many things, such as portals, mirrors, and more, but an easy feature to implement is outlining of models, so let's take a look at that. We first want to render our object like we normally do, and update the stencil buffer with 1s everywhere we have a fragment from our object, and 0 everywhere we do not have a fragment from our object. This will essentially create a figure like this. Then we want to disable writing to the stencil buffer so we do not accidentally modify it, and also disable depth testing so that we can make sure the next object we draw will be completely in front of the previous one. Now we want to render a scaled up version of the object we had before, but this time in a flat color and with the following condition. We only draw its fragments where the stencil value is not 1, so basically not where the silhouette of the previous object was. Then we just restore writing to the stencil and enable the depth buffer again. That's all we have to do. Now let's implement it in code. We start off by enabling our stencil buffer using enable glStencilTest and making sure we also have our depth buffer enabled. Then we use glStencilOp, plugging in glKeep, and glReplace. This will make it so that when both the depth and stencil tests pass, we'll use the reference value specified by glStencil function. Now let's make sure we clear all the buffers before each frame and go on to the part where the magic happens. First, we specify our stencil test always passes and set the reference value to 1. Then we enable writing to all of our stencil buffer with a stencil mask of all 1s. And now we simply draw our object. By this point in time, our stencil buffer looks like this and our color buffer looks like this. Remember that all these values are 1 because we specified in the glStencilOp function that if both the stencil and div tests pass, then make the pixel of the stencil buffer equal to 1. Now for the outline, we want our stencil test to only pass when it's not equal to 1 and the div test passes. Then we disable our div buffer for previously mentioned reasons and disable writing to the stencil mask so we can keep our original silhouette. Now, since we want to make the outline a flat color, we'll have to create 2 new shaders and the shader program. So let's first create the shader program like so. Then for outlining.frag, we simply want to return a color, while for outlining.vert, we want to get a position and all the uniforms related to transformations, plus a new float uniform called outlining, which will multiply with the scale matrix. Now back in the main function, we'll want to send that outlining uniform to the shader with a value of something like 1.08. Then we simply draw the same object again, but this time using the other shaders. The last step we need to do is to enable writing to the whole stencil, clear it by always passing the test and replacing the values with 0, and enabling the div buffer. Now, if you run the program, you should see an outline around your object. If your object has its origin at its geometrical center, and if it doesn't have very complex shapes, then the outline probably looks fine. In my case though, you can see that the origin is not at the center since the outline is skewed upwards and that the shapes are pretty complex with many curves. Therefore, this method won't work that well. A better method that doesn't take much would be to import the normals in the vertex shader and add these to the position vector, multiplying them by the outlining, which will remove from the scale matrix and which will now lower from 1.08 to 0.08. Now when scaling the vectors, instead of scaling them from their origin, we are sort of scaling them outwardly from the model using the normal as a reference for what outward means. This will give you much better results with one exception. If you have hard edges, then your normals will be close to perpendicular to one another and so will create a little gap when expanding the model. Therefore, a third solution to this would be to simply have another model that's bigger than the first one. To be more specific, it has to be thicker, not necessarily bigger. You can achieve something like this using Blender's Solidify modifier. Here you can see I have the initial model and the bigger version of it. Now I've already exported both as different models and I only have to import them into my program like so. Then instead of drawing the object a second time, I simply draw the bigger version of it, this time not even needing a uniform to scale it. And as you can see, this gives the best results, though at the cost of doubling the storage cost. You could of course make a function similar to the Solidify function that Blender has, but that would be a bit slightly more complicated for this tutorial. That was it for this tutorial. As always, the source code is in the description. Bye!